Hi everyone, my name is Anshita Jain and I am a pre-final year BTech Engineering Physics student at IIT Roorkee. Today I'll do a presentation on the topic image compression techniques. So let's start. Now, what is an image? An image is a matrix of pixels, a 2D matrix of pixels, which represents visual information. Each pixel holds a color or intensity value. In grayscale images, it can vary from 0 to 255 depending on the brightness of the image. And in colored images, each pixel has three components corresponding to it called RGB or red, green, and blue. Now here we have a sample image as you can see. This is a very zoomed in version of the image. So you can see these pixels, these tiny boxes. These are the pixels. And this is the matrix form of the pixels. So for example, for this particular pixel, the value is 10. And for this particular pixel, the value is 70. Now, what is image compression? So, image compression is basically reducing the amount of data which is required to store a particular image. And there are two types of image compressions, lossless and lossy. So, in lossless image compression, no data is lost and the original image can be restored. Whereas in lossy compression, there is some loss of image quality for better compression ratios. Now, why do we need to perform image compression? Firstly, less storage space is required if the image is compressed. Also, it is easier to process images and transmit them over the internet if they are compressed. So, image compression techniques. In this presentation, I have covered mainly two kinds of image compression techniques. The first one involves convolution, and the second one involves performing Fourier transform and then applying a low pass filter. Now let's go through them one by one. First one, we have image compression using convolution. So what is convolution? Convolution is a mathematical operation which basically involves sliding a kernel matrix over an image to transform it on the basis of local pixels. Now let's take an example. So this is an input image and this is the kernel. Now for this particular pixel, what we did is we formed a 3 cross 3 matrix using its neighboring pixels, which is the same size as the kernel. And we performed element-wise multiplication, that is 0 into 1 plus 0 into 0 plus 0 into 1 and so on and so forth. And then we added all of them to obtain this, that is 3, the final pixel value. And this is the mathematical form of convolution. Now, predictive coding. So, in predictive image coding, convolution of the original image happens with the kernel to generate a predicted matrix, and then a residual matrix is calculated to achieve image compression. Let's go through the steps one by one. So, the first step is convolution. The image is convolved with the kernel, as I already mentioned, and we obtain a predicted matrix. Okay. Now, after obtaining the predicted matrix, we calculate the residual matrix, which is basically obtained by subtracting the predicted matrix from the original image. Now, this residual matrix basically captures the difference between the original pixel values and the predicted ones. Okay, and usually they are very small and can be encoded very efficiently. This is the mathematical formula. Image actual minus image predicted is the residual image. Now, we can also reconstruct the original image. For that, all we have to do is add the predicted image and the residual image, and we can get back the reconstructed image. So this is a lossless form of compression. Now, how does this help in compression? Like, how is this compressing the image? So firstly, reduced entropy. Both the predicted matrix and the residual matrix store lower amount of information. That is, they can be stored using very few bits. Also, sparse residuals. The residual matrix is sparse, that is, it comprises mainly of zeros, and there are very few non-zero values, which leads to easier storage of the residual matrix. Also, storing the smooth predicted matrix separately from the residual details results in a higher compression ratio rather than directly compressing the original image. Now, in this presentation, we'll use the Gaussian kernel, which is obtained from this Gaussian function, as you can see, and it is represented in the 2D matrix form as this. And it can also be normalized. So for normalization, we simply add a all of the elements of this matrix, and then we divide it by that to obtain this normalized form of the Gaussian kernel. Now, why are we using Gaussian kernels? So Gaussian kernels are used because they preserve the smoothness and natural structures in an image. Also, they capture the general trends of the pixel values very well, and they leave out all the sharp changes or edges as residual. Now, let's take an example because it's always easier to understand things using examples. So here I took this image, okay, which has only two colors, pure black and pure white. So this is the matrix form of that image. That is, all the black region can be represented as zeros, and the white region can be represented as 255s. So this was the matrix form. Now we'll perform convolution. But as you remember, while performing convolution, each pixel has to have neighboring pixels, but in these border pixels, as you can see, they don't have they have less number of neighboring pixels. Like this one only has three. The upper and the left ones are missing. So for this we have a solution. We add zero padding, which is basically a border of zeros, to keep the image dimensions consistent after applying the filters. So this is the zero additional border that we added to the image to keep the image dimensions consistent. And then we perform convolution. So here is the sample calculation. For example, for this particular pixel, first we'll form a 3 cross 3 matrix using its surrounding neighboring pixels, which is this matrix. And then we'll apply the Gaussian kernel. And then we do element-wise multiplication as earlier, that is 0 into 1 plus 0 into 2 plus 0 into 1 plus 0 into 2 plus 255 into 4, and so on and so forth. And then we add all of them to obtain this final value. And since we are using the normalized version of the Gaussian kernel, we'll divide it by 16 to obtain this final value of the pixel in the predicted matrix. Now, after performing convolution over the entire image, we obtain this final predicted matrix, and this is the matrix in the image form, as you can see. And then we calculate the residual matrix, which is basically the original matrix minus the predicted matrix. And this is the image form of the residual matrix. So the original image, the predicted image, the residual image, and the restored image, which is simply obtained by adding these two again. Now here is a Python code to implement the same. First, we load the matrix as a NumPy array and also the kernel as a NumPy array. And then we perform convolution, and then we calculate the residual image and the restored image, and then we plot all of them. We can also apply this on a JPG image. So this was the original image. This is the predicted image. As you can see, there are some smoothened areas, even though the difference is very less, but it is slightly blurry, and the some of the areas have been smoothened. And this is the residual image. As you can see, it stores all of the sharp edges of the image. And this is the restored image, which is obtained by adding these two again. Now here is a Python code to implement the same. It is the same as the previous one. The only difference is that here we are performing the convolution of a JPG image with the kernel matrix. Earlier it was simply a NumPy array. Here it is a JPG image. Rest everything is same. Now next we'll come to image compression using Fourier transform. So firstly, what is Fourier transform? It is a mathematical transform which basically converts a signal, or in this case an image, from the spatial or the time domain to the frequency domain. Now this is the mathematical form of discrete Fourier transform for a 2D signal or a 2D matrix. Now, what is the frequency domain? So in frequency domain, each point represents a particular frequency contained in the spatial domain range. And low frequencies correspond to slow variations in pixel intensity like smooth areas, whereas high frequencies correspond to rapid changes like edges and noise. So this is the representation of this original image in the Fourier after performing Fourier transform in the frequency domain. And next we'll discuss low pass filters. So what are low pass filters? A low pass filter removes high frequency details which are less noticeable to the human eye by keeping only the low frequency components of an image. And since this leads to reduction in the amount of data, compression of image happens. This is an example of a circular low pass filter which can be represented in the mathematical form. Now, what are the steps of image compression? So the first one is we convert the image to grayscale for simplicity. Then we perform Fourier transform to convert it into the spatial domain. After that, we apply the low pass filter. And after applying the filter, we perform inverse Fourier transform to reconstruct the image in the spatial domain. And then we obtain the compressed image, which is reduced in detail and in size as the high frequencies from the image have been removed. The image still retains its overall structure, but with fewer data points. Now, let's take an example. So, in this particular example, we are taking this image. Okay, it can be represented as a 5 cross matrix, 5 cross 5 matrix as this. Now first we perform Fourier transform and obtain this matrix in the frequency domain, and this is the representation of the image in the frequency domain. After that, we apply this particular low pass filter and obtain this filtered version of the image in the frequency domain. So this is the filter, and this is the application of the filter on the image. This is the image after application of the filter in the frequency domain. And then we perform inverse Fourier transform and finally obtain our compressed image in the spatial domain. So this is the image representation of the matrix. So this was the original image, and this is the compressed image after low pass filtering. Now here is a Python code you can use to implement the same. We first take the original matrix as a NumPy array, then we perform the Fourier transform, then we apply the slow pass filter, and then we perform the inverse Fourier transform to obtain the compressed image, and then we plot all of them. We can also apply this on a JPG image. So we take an image, then we obtain it in the frequency domain, then we apply a low pass filter mask, and then after applying this mask, you can see the filtered version of the image in frequency domain. And when you come back to the spatial domain, there is a compressed image, that is in the spatial domain it has been compressed after the removal of the higher frequency components. Now here is a Python code to do the same. It is the same as the previous one. The only major difference is that earlier we were performing all of those operations on a NumPy array. Here it is a JPG image, which is again a matrix. So all those steps are repeated. It is converted into a grayscale image, and then we perform a Fourier transform, then we apply the mask, and then we perform inverse Fourier transform, and then we plot all of the images. Now, what are the real world applications of this? So, in JPEG image compressions, discrete cosine transform is used, which is quite similar to discrete Fourier transform. That is, images are transformed from spatial domain to frequency domain, and then the higher frequencies are removed. Another application is in video streaming platforms like Netflix, YouTube, etc., where both predictive coding and discrete Fourier transform are performed. To efficiently encode the video data, the quality, and the bandwidth usage. Another famous application is medical imaging, that is CT scans and MRI scans. So, both low pass filters and DFT are employed to reduce the noise and improve the image quality, while the image clarity, while keeping the data size manageable. So in this presentation, we mainly covered two image compression techniques. The first one was predictive coding, which involved convolution, and the second one was discrete Fourier transform, after which we performed low pass filtering in the frequency domain. Now, both of these techniques are quite efficient, but predictive coding is usually used where is redundancy in the spatial domain. That is, there are many repetitive pixels in the spatial domain, and we perform discrete Fourier transform and low pass filtering when there is frequency based redundancy, that is many frequencies are repeated in the frequency domain. So in that case we perform DFT and low pass filtering. So this was all about various image compression techniques and their applications. Thank you so much for watching this video. I hope you could understand everything. Thank you.